Okay, so yesterday I have explained the general framework of the topological quantum chemistry of the symmetry-based indicators. And I also discussed examples in one and two dimensions. So today I will continue this topic and discuss an example in 3D. Then I will move on to the classification of spin space groups. So now let's start the indicator in 3D. So we remember that in 1D, in a 1D space group with inversion symmetry, we have a classification, we have a trivial classification, right? And in 2D, we have a Z2 classification, and this Z2 is just the parity of Chen number, right? And in 3D, the classification turns out to be a bit more complicated. We find that the classification is 3 Z2 factors and a Z4 factor. Now let me explain what this classification means and what topological states they correspond to. So first, in as I have explained the algorithm, how to derive this and how to start with the EBRs in real space. So now I just skip this step. I just talk about the momentum space. So let's consider the 3D Brilliant zone. It's a cube. And in this Brilliant zone, we have 8 high symmetry momenta. It's given by 0 or pi, 0 or pi, 0 or pi. So we have 8 high symmetry momenta in total. And we can apply the algorithm I introduced yesterday to obtain the expressions for the symmetry-based indicators. And so now I can, so I just skip all this process and just give the result. So the 3 Z2 factors are given by indicators of this Z2I. This 2I just means it's Z2 valued. And this I takes values in X, Y, and Z. And it's defined by this expression. Sums over all the momenta with its ith component equal to pi. Sums over all the high symmetry momenta with its ith momenta equals to pi. And we count the number of odd occupied levels, and then we mod 2. So these are the 3 Z2 factors. And the Z4 factor is given by this eta 4i. So basically this 4 means it's a Z4 valued indicator. And its expression is given by the number of occupied odd levels over all the high symmetry momenta and mod 4. So these are the results. Let me explain the physical meaning of these indicators. So first, these 3 Z2 factors are easy to understand. As we have established yesterday, for a two-dimensional system, if we have a Chen number, then there is a relation like this. Then we have this relation. C equal to the parity of the number of occupied states with an odd parity, right? So we established this relation. So then we can see that this expression is nothing but just a trivial generalization of this indicator we talked yesterday. But this Z2 this Z2I is are defined on different planes. For example, this Z2IX counts the Chen numbers on this plane, on this Kx equals to pi plane, right? So it's the parity of the Chen number in this plane. And the Z2IY, this is X, this is Y. So it counts the Chen number in this direction. So basically, this Z2IX equals to Cx mod 2. And this Z2IY equals to Cy mod 2. So basically, the first 3 Z2 indicators are just just indicates the 3D Chen insulators. And so if you are a bit confused of this result, maybe I can explain a bit more. So let's consider how to construct a 3D Chen insulator. So we can start with a 2D Chen insulator in the perpendicular to the x direction. This is the real space. This is y. This is z. Okay. So we have a Chen number 1 here, and then we put a copy of this 2-dimensional Chen insulator at another x position. So this one locates at x to 0. This one locates at x to 1. And then we copy another one. And we continue this to infinity. And now we have a 3D system which is decoupled to 2-dimensional layers. And actually, the 3D Chen insulator is adiabatically equivalent to this stacking of layers. And now if you transform this states into momentum space, you will have the parities in momentum space like this. Let's assume in each layer we only have a single occupied band. So in the 3D system, we also only have a single occupied band. And as these layers are decoupled in the x direction, nothing depends on kx, right? So kx is just a trivial index here. And the parities can be simply like this: minus, plus, 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 minus, plus, 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 right? So this parities does not depend on kx. So kx equal to pi and kx equal to 0 have the identical parities. And if we understand these parities as the eigenvalues of the 2-dimensional system, it's just simply a 2D Chen insulator. Yeah, so by this, I think I have explained the meaning of the Z2 indicators. Now let's move on to the Z4 indicator, eta 4i. As I have explained yesterday, the way we define the BS set or the way we define the B vectors only guarantees that the band structure is gapped along high symmetry paths, right? Nothing guarantees it can be gapped everywhere in the Brillouin zone. So we can imagine that some indicators may correspond to some topological semimetals rather than topological insulators. This situation never happens in non-magnetic materials or in the space groups with time reversals. But if we consider magnetic space groups, this indeed happen. And this eta 4i is just an example. So now let's consider this thing. Let's consider eta prime defined as eta 4i mod 2. Okay, let's further mod this eta 4i indicator, and let's see how we can understand this indicator. So it can be written in this form: k equal to gamma x y m nk minus k sums over ZUTR. Let me explain the notation. ZUTR basically the momenta at the kz equal to pi plane. So this is x, m, y, gamma. This is Z, U, T, R. Okay, so these four momenta are just high symmetry positions at the kz equal to pi plane. And we sums over all the occupied odd levels, and then we mod 2. So you may wonder that why this operator becomes minus. Before it was plus. The reason is that here we have a mod 2, so they are equivalent. So anyway, we can put this eta prime in this form, and remember that this quantity is nothing but the parity of Chen number at the corresponding kz plane, right? So this is just the kz. Sorry, how to say this? This is just kz equal to 0 mod 2. And this is kz equal to pi mod 2, right? So we can compute the Chen numbers at the two different planes. And now, if this eta prime equals to 1, that means these two planes have different Chen numbers, right? So, and now let's, actually we can consider the kz as a parameter of a two-dimensional system, right? We can write the 3D Hamiltonian in this way, kx, ky, and kz. And we can regard this kz as a tuning parameter of a two-dimensional system. So we know that when kz equal to 0, the two-dimensional system may have a vanishing Chen number. But when kz becomes pi, this two-dimensional system has a Chen number 1. That means there must be a phase transition point at some kz, right? And that phase transition point is just is a well point. So basically, when eta prime equal to 1, we have something like this. So this plan, so this is kz equal to pi plan, has a Chen number 1 maybe. And the other plan has a Chen number equal to 0. And in the middle, between them, there must be a phase transition point. It's a well point. And basically, we can understand a well point as a monopole in momentum space, right? So any surface, you plot any surface to surround this well point, and the barrier curvature integrated over this surface must equal to 1. So that gives the difference between Chen numbers at the kz equal to 0 and kz equal to pi planes. So now we have explained that when eta 4i equals to 1 or 3, which means eta prime is 1, the corresponding band structure is not a topological insulator, but a topological but a well-sand metal, right? So it corresponds to well-sand metal.
But it cannot be in a generic point, right?
Yeah, it's at a general point.
It doesn't need to be predicted by some symmetry.
Yeah, but because in this example, I only consider the inversion symmetry. So yeah, you are correct. If we consider more symmetries, like if there is a C4 symmetry, then this well point must be pinned at some high symmetry line, like the C4 axis, right? Yeah, but in our framework, if C4 is included, then we will avoid this to happen because of the compatibility relation, right? Yeah. Yeah.
If you want to impose the diameter, so it has to be
right. Let me consider. If I think if we impose time reversal symmetry to this model, it's still a well-sand metal.
Several points.
Yeah. But in that situation, this well-sand metal is no longer detected by the symmetry eigenvalues. Yeah, when time reversal present. Okay, so the only remaining case is eta 4i equal to 2, right? So this is the only remaining states we do not understand yet. Yeah, sorry, model 4. I can directly give the answer, and then I explain how this is derived. So we can design an insulator to have parities like this: minus minus, plus plus, plus plus, plus plus, plus minus, plus minus, plus minus, plus minus. Now let's count the number of all the parities. So the kz equal to pi plan contributes nothing because we have 4 there, and after model 4 there is nothing. In the kz equal to 0 plan, we have only 2 all the levels, so that contributes to the eta 4i equal to 2. So if we can make a model like this, it will realize this symmetry indicator. So the question is, what topological insulator correspond to such parities? So actually the answer is very simple. Let's consider again a layer construction in real space. So this is a z-axis, and these numbers are just the values of z. So it's so this is the unit cell. The unit cell has a length of 1. So now let's consider to put a chain insulator in the in the z equal to 0 plane with a chain number equal to 1. Okay, with the chain number equal to 1. And then we put another chain insulator at z equal to 1/2 with the chain number equals to -1. And then we continue this. C equal to 1, C equal to -1. Okay, so now let me explain why this construction corresponds to a parities like this. So remember that for a 2-dimensional chain insulator with an odd chain number, the parities can have this pattern, right? Can have this pattern, gamma x y m, right? And remember in the first lecture yesterday that when we do the Fourier transformation for these states, there a phase factor might appear due to the position of the orbitals we consider, right? So remember that we would have this phase factor in addition to the parity of the orbitals, right? So now let's first transform the layers at z equal to 0 to momentum space. Then that means this T alpha is 0, and this phase factor does nothing. So this chain insulator will simply contribute to identical parities at the 2 planes, right? So it will contribute to parities like this, in this way, right? Because this layer has T alpha equal to 0, so the parities the inversion eigenvalues does not depend on the value of kz. So we have identical parities at the 2 planes. But now let's consider the layer at z equal to 1/2. So for this layer, the T alpha equals to 0, 0, 1/2. Sorry, this is 2 pi. Sorry for this. This is 2 pi. So for this layer, T alpha is 0, 0, 1/2. So that means when kz equals to pi, we will have an additional minus sign for all the parities. Maybe the notation is a bit confusing. Let me write it more clearly. So this additional phase factor should be e to the I g dot T alpha. Okay, and g is defined by k minus k. Okay, so for the inverse invariant momentum, k could be 0 or pi, right? When k is pi, then this g is just 2 pi, right? So this 2 pi times this T alpha equal to 0, 0, 1/2 for the layer at z equal to 1/2, we have an additional minus sign, right? And so considering this additional phase factor, okay. So considering this additional phase factor, we can have parities like this. So these parities are just Kc alpha. And this parities is given by Kc alpha times this additional phase factor, right? So this phase factor is -1 for the layer at z equal to 1/2. So it flips all the signs of these parities. But for the layer at z equal to 0, the phase factor is just 1. So this case is much more simple. So the 2 layers have the identical parities. And if we sum over the 2 layers, we reproduce these parities, right? We reproduce the parities I showed at the beginning, right? So this eta 4i equals to 2 actually correspond to a layer construction of chain insulators with with alternate. I don't know how to say it. It's with this changing sign, right? it's a layer construction in this way. So it's very simple to understand in real space. But you may ask what kind of topological insulator this construction is. I can answer this question in two ways. First, we can look at the topological response in the bulk, and second, we can look at the boundary states. So this insulator is actually referred to the Anxion insulator. Let me explain why this construction is an Anxion insulator. Now let's consider a layer construction with an even number of layers. So let's say it's C equal to 1, C equal to minus 1, C equal to 1, C equal to minus 1. I just plot 4 layers, but I mean there could be infinite number of layers, many enough layers, right? So anyway, it's an even number of layers. So to see its Anxion insulator, we consider to apply a magnetic field in the z direction, okay? And we examine the magneto-electric response. So the defining character of an Anxion insulator is the quantized magneto-electric response. It's written in this form. So if you apply a magnetic field, it will introduce electric polarization in the same direction. And the coefficient is given by theta over 2 pi up to some universal constants. I don't remember those constants, but basically it's theta equal to 2 pi, theta over 2 pi. And in an Anxion insulator, theta is quantized to be pi. So this is the defining feature of an Anxion insulator. Now let's see whether it's the case for this layer construction. So now let's apply a magnetic field in the z direction, okay? And if you are familiar with the properties of quantum Hall states, you know that there is a Zhida formula. The density of a layer the change of the density in a layer is proportional to the Chen number multiply the magnetic field. So CL times partial TB. So this CL is the Chen number of the layer L, and if you do the integral along time, you obtain this, right? So when you apply the magnetic field, you introduce extra charges at different layers, and as the Chen numbers have different signs, so basically this delta rho for the first layer, because C is negative, so delta rho for the first layer is negative, and the delta rho for the second layer is positive, right? And negative and positive. And you see you introduce a net polarization in the z direction. And the coefficient is simply 1/2 because the polarization is basically defined by the position of the charges and the number of the charges, right? And so basically the distance between the two charges is 1/2. It's 1/2 of the unit cell. So we obtain that this P equals to 1/2 times B. So this is exactly the defining feature of the Anxion insulator. So now we have argued that this layer construction is just an Anxion insulator, and this eta equal to 2 mod 4 is the indicator for Anxion insulator. Okay, so this is the response in the bulk of an Anxion insulator. We can also examine its topological surface state. Okay, to see this, so to see this surface state, we have to preserve the inversion symmetry. So actually, this is a bit subtle. In the previous argument, we have said that we have an even number of layers. This layer construction must break inversion symmetry because the inversion center locates at some layer. So if you have an even number of layers, you cannot find a global inversion center. So this construction actually breaks the inversion symmetry. The reason is simple, because if the finite size sample indeed preserve the inversion symmetry, we can prove that the surface state must be gapless. And if you have a gapless surface state, then this magnetoelectric response is ill-defined. Okay, so now let's consider a sample with inversion symmetry. So for simplicity, we put the Borg Hamiltonian in a sphere that respects the inversion symmetry. Okay, and we can imagine that the layers will have many crossings with this sphere surface, and for each crossing, we plot this line, and this line, because the line corresponds to the edge of a chain insulator, so at this line, so we have Carroll edge modes, right? It's just the edge state of the two-dimensional layers. So if this geometry respects the inversion symmetry, then there must be equal number of edge states on the on the upper half and the lower half, right? And but the edge state in the middle is special. This one, the middle one, itself is invariant under the inversion operation. So now let's consider a continuous deformation for this Hamiltonian. We can consider to dimerize these Carroll and anti-Carroll states on the surface. So when we dimerize these two states, they gap each other out. So basically, they kill each other. So you won't have this after we pair it. And symmetrically, when we pair the modes on the upper half, symmetrically, we must pair those in the lower half due to the inversion symmetry. So after we do this pairing, the remaining boundary states is simply a single Carroll edge mode at the equator of this sphere, right? So this is the only remaining edge state. And then, as long as you preserve the inversion symmetry, you cannot gap these states out. For example, if you want to push these states toward in the positive z direction, then you must push some other z state in the negative z direction. So you will never, you can never remove this Carroll 1D state on the surface. So actually, this is the bulk boundary correspondence for the inversion protected axion insulator, and this is a bit different compared to the conventional bulk boundary correspondence, because usually if you have a topological insulator in 3 dimensions, then its topological surface is a 2-dimensional state. But now we have a 3D topological axion insulator, but its boundary state turns out to be 1-dimensional. So we say it has a d-2-dimensional boundary state. Surface state. So, and this is the definition feature of a higher order topological states. So, so that means the axion insulator protected by inversion symmetry is in fact a higher order topological insulator. Okay.
Can you explain a little bit again or in another way why is 2 minus 2 dimensional and not just an edge?
You mean why the surface is d-2 dimension? Okay, so the bulk Hamiltonian is 3 dimensions, so d equals to 3, right? And now we have a sphere geometry, and we argued that the gapless surface state is this 1-dimensional Carroll edge state. So the surface state, so the dimension of the surface state is 1. So this is 3 minus 2 equals to 1. So the surface state has 2 dimensions lower than the bulk Hamiltonian. So this is unusual compared to the conventional topological insulators. So that's why people call it a higher order topological insulator. Okay. Yeah.
Yeah. In the previous section, can you say why the constant for the polarization is 1/2 instead of 3/2? Because it seems like you're essentially pumping charge from the bottom to the topmost layer, right?
Yeah. Yeah, I think we can do some. yeah, I don't remember the full details, but the idea is that you can count the change of charge on the top layer, so it corresponds to the chain number and also the area of the top surface, and you can also count the change of the charge in the bottom layer in a similar way, and then you divide by the distance between them. Actually, I don't remember the full details, but doing calculation like this will correctly reproduce this 1/2 factor. Yeah. Maybe I can check this later and explain it to you. Okay, so basically this is the end of my first question.
So in the bottom, when you put it on a sphere, you have an even number of layers?
Odd number of layers, because the even number of layers must break the inversion symmetry. Yeah. Yeah, okay.
I have a question. Can you give an example of how that would look in a real material?
So in reality, a material never looks like this. Yeah. So, but fortunately, usually in a realistic material, there are many other symmetries, like mirror symmetries and C3 symmetries, and those symmetries will pin this hinge mode at particular directions. So that means as long as you cut the crystal, you can make the particular corner of this crystal, you will observe this hinge mode. Yeah, but here I only assume inversion symmetry, so nothing can determine the position of this hinge mode, right? Okay, so this is the end of my first lecture. In the remaining 20 minutes or 20 minutes, I will briefly talk about the classification of a spin space group. Okay.
You don't need it anymore.
No, thanks. Okay, I forgot to introduce the references for TQC and the symmetry indicator at the beginning, so I show it now. So basically, the first two papers invent this idea, and after that, there is a wave of follow-up works. Yeah. And if you are interested in this reference, you can take a picture. Okay, so now let me move on to the spin space groups. These are my collaborators. This work is mainly done by the student Zhenyu Xiao. So let me first give the definition of a spin space group. So now so we start with a non-magnetic material that is described by a simple space group. So for this molecule, we have the C3 rotation symmetry, right? And if there is a spin optic coupling, then this spatial operation is no longer a symmetry of the system, because when you do rotation for the atoms, you must rotate the spin at the same time, and these spin operators will change the structure of this group from a single valued group to a double valued group, and then if the system has instability towards magnetism, then after the phase transition, you have some local moments on these atoms, and then not all the symmetries in this double space group still apply after this symmetry breaking. Only a subset of symmetries remain. And this remaining subset forms the magnetic double space group. Actually, this is the usual way how we understand a magnetic material. Actually, there is another path from this non-magnetic material to this magnetic material. So we can imagine such a situation where the spin optic coupling plays a minor role compared to the to the polarization of the magnetic moments. So that means we can treat the spin-optic coupling as a perturbation effect. It's small compared to the exchange energy of the magnetism. So if this happens, we can first turn on the magnetic order without any spin-optic coupling, and then in this case we find that the symmetry group could be much larger than the usual expectation. For example, in a usual magnetic material, when we rotate the atoms in real space, we must rotate the spin in the same way, right? So, for example, here we rotate the atoms by 2 pi over 3, then we must rotate the spin also by 2 pi over 3. But if there is no spin-optic coupling, it's possible that the spin behaves in some other way. For example, here, when we rotate the atom by 2 pi over 3, we rotate the spin by minus 2 pi over 3. This would not be a symmetry if the spin-optic coupling is considered. But as long as spin-optic coupling is plays a minor role here, or it's a perturbation, we could treat this as a symmetry. We call this spin space symmetry. And this spin space symmetry was first realized in 60s and 70s. I think it's quite early. At that time, people used this spin space symmetry to understand some extra degeneracy in the magnum excitations. And in recent years, this concept may cause more and more attentions. For example, in the so-called automagnetism, and in some novel topological states protected by such symmetries. A problem is that this spin space symmetry is never classified. So it's never fully classified. So our work try to fully classify all these symmetries. And so let me first define a spin space group, okay? So let's first consider a magnetic structure given by this S. Maybe I can write. So a magnetic structure is defined by a classical vector field, right? S is a vector, and it's a function of R, so it's a classical vector field. So it describes a magnetic structure. And we can consider operations in this form, in this XU RV form. This RV is just a spatial operation. R is a rotation or inversion. V is a translation. And the XU is an operator only acting on the spin structure. So basically, you can, as we understand the S as a classical vector field, you can understand the XU as a 3x3 matrix. So we define this operation, and its action on such a spin configuration is defined in this way. So the spatial part only acts on the position, and the XU part acts on the spin. So you can just omit this small s. You can just treat XU as a 3x3 matrix. So this is the definition of the operation of a spin space operator. And the spin space group is given by the collection where all the elements leave a given moment configuration invariant. So this is the definition of a spin space group. So it looks a bit complicated, and it seems it's not direct to classify all these symmetry groups, but it turns out to be very simple. So now let's consider 3 atoms in the system. So let's consider we have atom A, atom B, and atom C. And if we just apply the spatial operation, let's say G1, it's a spatial operation, sends A to B, and G2 sends B to C. And also there is a G3 sends A to C. So we immediately know that G3 must be given by G2 times G1, right? So this is a space group. All these are space group operations. So now let's try to find, now let's assume there are some momenta on these atoms. Now for each of these operations, we need to assign a spin operation. It's a 3x3 matrix, it's X and U, that transform these spin vectors correspondingly. So let's say we assign our operator O1 for G1, O2 for G2, and O3 for G3, okay? So it's clear that this vector is given by O1 acting on this vector, right? And this vector on C is given by G2, O2 acting on this vector. And similarly, this vector can also be obtained from the vector on A by acting O3. So it immediately follows that there must be this relation, right? This is very direct, right? So the algebra must be closed under these operations, right? And remember that actually this relation applies to all the operations in the space group, right? And remember that this O is just the 3x3 matrix. So now for each spatial operation, we have a 3x3 matrix OG. And this OG satisfies the exact same multiplicity table as the spatial operations. So what's this OG? It's just a three-dimensional representation of the group, right? So it's by definition a three-dimensional representation of the space group. So the classification problem becomes a very simple problem. It becomes a problem to enumerate all the possible three-dimensional representations. And so after regularizing this, we can formulate this problem in a very simple and nice form. So for example, for a generic non-collinear structure, we only need to find all the possible 3x3 matrix, all the three-dimensional representations. There are still some subtleties. For example, sometimes the magnetic moments may locate in some plane. So in this case, we see the magnetic structure is coplanar, but they are not collinear. So in this case, all these vectors are in a plane. So we only need to find the 2x2 matrix to rotate this for the spin operations, right? Because we only have two directions for the spin. So in this case, for the coplanar case, we only need to find all the possible two-dimensional representations, right? And similarly, if all the moments are collinear, we only need to find a one-dimensional representation, right? So the framework is very simple. So now let me give you a few examples. So let's consider the space group. Maybe I can stop after this example. Okay. So let's consider the space group P3. It's a simple space group with a C3 rotation symmetry. And at first, we consider the trivial 3x3 representation. It's the identity representation. So that means when we rotate the atoms, we do nothing to the moments because the spin operator is identity, so it does nothing. So all these atoms locate at the C3 invariant positions. All the three, the yellow, the blue, and the black atoms, all of them locate at C3 invariant positions. And so when we apply C3 operations, for example, centered at this black momentum, we do nothing to the moments. So the moments can align in any direction. Yeah. So basically for this symmetry, you just put random directions. So this is one possibility. And then we consider another a non-trivial example. Let's consider a one-dimensional representation of the group. We consider this representation A1. It's labeled by the momentum 0, 0 pi. And its representation matrix is defined by these two equations. And the C3 is identity. And the translation, it's either 1 or -1, depend on the parity of T3. T3 is the component along the z direction. But this is a one-dimensional real representation. To form a three-dimensional representation, we simply put two trivial representations, two identity representations. So this is a 3x3 spin operator. And we notice that under a C3 rotation, we do nothing to the moments. But under a translation, if the T3 component of the translation is odd, we put a minus sign for the Z component of the moments. So that means if we have this structure at Z equal to 0 plan, then at the next plan, Z equal to 1, all the Z components of the moments will be flipped. Okay? So the only change between the second layer and the first layer is the change of the Z direction, is the change of the Z component of the moments. So, and we can continue. So this is another, so this is a magnetic structure described by a different spin space group. And this spin space group is characterized by the A1 representation of the space group. Now let's continue with some more non-trivial examples. So let's consider a two-dimensional representation. So let's consider this gamma 2, gamma 3 representation. Actually, this gamma 2 representation has a complex eigenvalue e to the I omega under the C3 rotation. And actually, this representation is not real. It's a complex representation. So to form a real representation, we must add its complex conjugation e to the minus I omega. And this representation is referred to gamma 3. So they together form a real representation. And we can apply some gauge transformation to this matrix to make it in this form. So the physical interpretation is also very simple. So under any translation, we do nothing to the moments. But under a C3 rotation, we also rotate the moments. But here we have this zeta can be either 1 or minus 1. It's arbitrary. Either way is either choice is equivalent to this representation. So if zeta equals to 1, it's just the usual magnetic space group. You rotate the moments in the same way as you rotate the atoms. But if zeta is minus 1, it's not a conventional magnetic space group. Actually, this is the situation I mentioned at the beginning. When you rotate the atom in some direction, you rotate the spin in the opposite direction. And then we consider an even more non-trivial example. We consider this delta 2 representation. Its C3 eigenvalue is identical to that of gamma 2, but it has a non-zero momentum. So that means when you apply a translation to the states, you get a phase factor e to the IU pi T3, and you can continuously change from 0 to 1. And so we can explicitly write down the representation matrix for the translation and for the C3 rotation. And it's a complex representation, so we need to add its complex conjugation, e to the minus u pi 2 T3 and e to the minus I omega. And we can apply the same trick we apply some matrix rotation, and to make both representation matrix to be real. And we find that when this is a spin operation assigned for the C3 rotation, it takes the same form as before. But the translation part is very interesting. When we apply a translation to the magnetic structure, we also need to rotate the moments by some angle. And this angle, u pi t, is defined by the momentum of this representation. So it might be worth emphasizing that this u could be a irrational number, right? And now let's consider what this means in real space. So when we consider the first layer, we only need to consider the constraint given by C3. So when you rotate the atoms, you also rotate the moments. That's it for the C3 constraint. And now let's apply translation to this structure. We translate the first layer to the second layer. And due to this spin operation, we must rotate the moments by a small angle defined by u pi. That means the global spin axis for the second layer is not the same for the first layer. It's rotated by this angle from the first layer, and every time you apply a translation, you have a global rotation for all these moments. And actually, this is a spiral structure, right? This is. It's not unique. So first as now we describe the spin structure as a classical vector field. We only consider 3x3 matrix. It's a real number valued 3x3 matrix. So we only need to consider a real representation. And the real representation is usually not irreducible representation of a space group. So given a irreducible representation, depends on its property. There are different ways to induce a real representation, and the basis of this matrix, as you mentioned, is not unique, but that's only corresponds to a global change of the spin axis for this material, right? So if you apply some basic transformation to this matrix, that's only corresponds to that you apply some rotation to the global spin axis. You rotate all the spin in the same time in real space. So we regard this rotation as, we regard the structures related by this global rotation as equivalent, right? Because they can deform to each other continuously without changing the structure, without changing the structure of the group, right? Okay. Okay. Okay.
There have been quite a few, but yeah, to be sure that we don't exhaust. There are other questions?
Okay.
Just a quick one. So, thanks for the talk. I was just wondering, so does the formalism allow, so the speed moment needs to live in a lattice site, or can it live in an interstitial site, for instance? I'm thinking of itinerant magnets where the spin might not be fully localized around an atom, but also in the space in between. So is this accountable in the theory?
I think it's the same. It's the same basically, because at the beginning when I define the spin structure, I just regard it as a vector field, where R is a continuous number, right? It's a continuous variable. In this plot, I just show it for simplicity. It's
Okay, thanks.
I'm wondering if all of this will work the same way or in a similar way for orbital magnetic moments.
As long as your orbital has some extra symmetry. So you see, in this framework, before the symmetry breaking, before we consider the magnetic structure, the global symmetry group is given by space group times a spin group, a spin symmetry group. A spin symmetry group here is SU2 or O3, right? And here we are just trying to find all the possible subgroups of that product group. So if your degree of freedom is not a spin but some orbitals, and if you want to find something like this, the question is that what's the global group before the symmetry breaking? And after symmetry breaking, you could find the symmetries in a similar way, I think. Yeah.
Thank you.
There are 4 minutes.
Okay, maybe I can explain a bit more how to. Yeah, I needed a few minutes to close this. So basically, I have explained that spin space group is characterized by some three-dimensional representations. So it seems that we only need to enumerate all the possible three-dimensional representations. But there is some subtlety here. We must module out the equivalence between different choices of the representations. For example, as mentioned by in the audience, there might be an arbitrary choice for the spin axis. So we will regard this as an equivalence. But this is simple to treat in this method because this arbitrary this equivalence just means we only need to find the inequivalent three-dimensional representations, right? So that's simple. And the second equivalence is very complicated to deal with in practice. So it's the equivalence coming from the arbitrary choice of the axis of the lattice. For example, for a C3, for a triangular lattice, you can choose your axis in this way, and you can globally rotate your lattice basis in real space by some angle, right? And all this should give a different choice for the basis should not give a different group. So we need to deal with this. This sounds simple, but this is very complicated in practice. And after module out, and we also need to consider the third equivalence. It's the equivalence of spiral angle. As I explained in this slide, the variable u here can continuously change from 0 to 1. And it could also be it could even be a irrational number. So in our framework, we won't regard structures with different u as inequivalent. So we regard all these groups as the same group because u can continuously change. So our third equivalence is the equivalence for the spiral angle. So after we model out all these equivalence, we obtain the classification of the spin space groups. Let me show you the result. Okay, so there is many of them. For example, for a non-coplanar case, we have more than 50,000 spin space inequivalent spin space groups. And for the coplanar case, we almost have 10,000. And for the collinear case, we have 1,421. Actually, this number is very interesting. If you are familiar with the magnetic space group, you may realize that this number equals to the number of type 1, 3, 4 magnetic space groups. And actually, following the logic how we classify the spin space groups, you may figure out that magnetic space group is nothing but given by the one-dimensional representation of the space group, where -1 corresponds to time reversal and 1 corresponds to identity. So these groups, these collinear groups, actually are isomorphic to the magnetic space groups. So when we do this work, when we obtain this number, we are quite confident that our framework is correct. Okay, that's it. So maybe I say a few more sentences. So we also examine the symmetries of magnetic materials in the database. It turns out that almost every magnetic material in the database have a higher symmetry than the magnetic space group. So it's not an artificial thing, this spin space group. It's very relevant in real materials. And it's also very useful when we want to compute some quantities like the spin textures. For example, for this material, if you look at its magnetic space group, it's quite low. And this symmetry basically tells us nothing about the spin texture. But if we look at the spin space groups, it's very high. Basically, no spatial symmetry is lost in this spin space group. And given this spin space group, we can immediately figure out that its spin texture is given by a particular representation of the point group, and it matches very well with the numerical results from DFT. Okay, that's the end of my talk.